Good day, class. So let's continue our lesson, the part 2 on AC circuit. So today we want to look at resistance in AC circuit. When you have a resistor connected in series with an AC source as shown above, the voltage and the current in the resistor, they are in phase. The voltage and the current in the resistor, they are in phase. What do we mean when that the voltage and the current, they are in phase? The voltage and the current are in phase because they attain their maximum position, their zero position, and their minimum position at the same time interval. For example, if you have a plot of the voltage and current on this axis against their time, current, this is our current and voltage axis. Now the current, let's say the voltage is doing that. As the voltage is doing that, this is for the voltage. Now the current as well will be doing the same thing. We move also in that direction. We move also like that. So this is our current. So you see, as they travel, the voltage and the current, they attain their maximum position. This is the maximum position for the voltage. This is the maximum position for the current, which is also known as their amplitude. So at the same time, you see, their maximum at the same time, and their zero position also at the same time. Their minimum position at the same time interval. So when the voltage and the current is doing this, we say the voltage and the current, they are in phase. They are in phase. That is, they attain their maximum position, their zero position, and their minimum position at the same instant in time, or at the same time interval. So the voltage and the current, they are in phase. So the resistor dissipates energy as heat. That is, the resistor consumes energy. The resistor consumes energy. Now from our Ohm's law, we know that V is equal to IR, where our V is our voltage, our I current, and this is our resistance of the resistor. Also, our average power or power will now be equal to voltage multiplied by current. So take note. So here is a question. So you are asked to find the current in the circuit above and the power dissipated in the resistor. Find the current in the circuit above and the power dissipated in the resistor. Now, how can you do this? Now, from our Ohm's law, we know that V is equal to IR. We are looking for current, so let's make current the subject of the formula. So current will now be V over R. Our V is, from the question, is 60 volts, and our arrow is 50 ohms. So when you divide that, you are going to get 1.2 ampere. 1.2 ampere as our current. That is the current flowing through the circuit. The part B now say, and the power dissipated in the resistor, VI. That is our power, voltage multiplied by current. So therefore, our power will now be, our voltage is 60, our current is 1.2. So that will give us our power to be 72 watts. Take note of that. I think that is simple. So now let's look at capacitance in AC circuit. Capacitance in AC circuit. As we can see, capacitance is represented by this symbol. Two parallel lines as shown there. and capacitance is measured in farad. Capacitance is measured in farad. That is F. Now, when the capacitor is connected in series in a circuit like this, the current and the voltage in the capacitor, they are not in phase. They are not in phase. They are out of phase. In fact, the current leads on the voltage by 90 degrees. And that is to say that the voltage lags on the current by 90 degrees. So here, current leads on the voltage by 90 degrees, or half pi over 2. And we can also say that the voltage, lags on the current by 90 degrees, or pi over 2. So take note of that. Now here, the capacitor, in this case, unlike the resistor, the capacitor does not consume energy from the circuit. So what the capacitor does is that it stores energy temporarily in its electric field and give back the energy to the source when the current decreases. So as the current goes up, it stores energy in its electric field, and when the current goes down, it releases the energy. So it does that temporarily. So the capacitor on its own does not consume energy. So it does not dissipate energy. It is the resistor that dissipates energy. So when we have a plot of current and voltage against time, we're going to have this. This is our current and our voltage and current axis. So as the current is doing that, so that is for the current. So we say the current here leads on the voltage, so by 90 degrees. So here is our 0, here is our 90, here is our 180, 270, displaced. Then here is our 360. A complete circle is 360 degrees. So here is our 90 degrees, 180, 0 degree. So now, this is for the current. That is current axis. That is the current curve. That is the current curve. So now the voltage will now move at this place. The voltage will continue its own at this place. So like that. As you can see, so here is 90 degrees. So now it means the current already reached the maximum position at this time, at this point, at this circle. So at this circle, the current already reached its maximum position. So the voltage is just picking up. So that means the current is what is leading on the voltage by 90 degrees. So take note of that. But we should know that a capacitor does not consume energy. Does not dissipate energy. But in real sense, there's no perfect capacitor. So there will be some, at least, little resistance in the capacitor. And that resistance, any resistance in the capacitor, that is known as capacitive reactance. Capacitive reactance. So capacitive reactance is the opposition to the flow of current offered by a capacitor. That is known as capacitive reactance, and it's represented by the symbol X subscript C. It's represented by the symbol X subscript C. That is capacitive reactance, and it's given by F subscript C is equal to 1 all over 2 pi FC. 2 pi FC. And don't forget our W is equal to 2 pi F. Our W omega, that is angular velocity or speed, is equal to 2 pi F. So this can also become 1 all over WC. 1 all over WC. So take note of that. Take note of that. And you can see from here that the frequency and the capacitive reactance, they are inversely proportional to each other. So as the frequency is increasing, capacitive reactance decreases. When you have a plot of capacitive reactance and frequency, if this was frequency, this is your capacitive reactance. You have a plot as this. So as capacitive reactance is increasing, frequency is decreasing. You see, in this case now, as frequency is increasing, capacitive reactance decreases. So that will be more current flowing through the circuit. So let's see inductance in AC circuit. As shown above, inductance in AC circuits. This is the symbol for inductance, and it's represented by L, a capital letter L. So an inductance is measured in Henry. Inductance is measured in Henry. That is H, capital letter H. And when an inductor is connected in series like this, in the inductor, the current and the voltage, they are out of phase. In this case, the voltage leads on the current by 90 degrees. So in the inductor, the voltage leads on the current by 90 degrees, or pi over 2 radian. That is to say, the current lags. So here also we say the current lags on the voltage by 90 degrees, or pi over 2 radian. So take note of that. The inductor does not consume energy in the circuit. What it does is that as the current increases and decreases, it stores energy temporarily in this magnetic field and give back the energy to the source when the current decreases. So it does not consume energy. Take note of that. Not be perfect. There's no perfect inductor. There will be some resistance in it. Just like the capacitor, just like the way I said in the capacitor. There will be some resistance in it that will oppose current, the flow of current. There's no perfect inductor. And the resistance offered by an inductor to the opposition to the flow of current, or the opposition to the flow of current, is known as inductive reactance. So inductive reactance, S subscript L. So this is what the opposition to the flow of current offered by an inductor, and it is given by SL is equal to 2 pi FL. Take note of that. So where your L is your inductance measured in Henry. So this is also SL is equal to WL. And you can see that the frequency is directly proportional to the inductive reactance. So when you have a plot of inductive reactance to frequency, you have your inductive reactance to frequency, you have a straight line curve. So that is to say, as the frequency increases, the inductive reactance in the circuit also increases. So as the frequency increases, the inductive reactance also increases. So high frequency signals will yield less current in the circuit, while low frequency AC signal will pass more current in the circuit. So take note of that. So here is a question. Said a 60 Hz AC signal at 120 volt is connected across a 500 millihenry inductor. You have to calculate the inductive reactance. Then 2, what is the current in the circuit? Now to do this, let's draw the circuit diagram for this question. So that is our inductor connected to an AC source there. So here our L from the question is our L here is 500 millihenry, while our voltage is 120 volts, and we have our frequency is our voltage. We have our frequency of 60 Hz. Calculate the inductive reactance. So our inductive reactance is L is equal to 2 by FL. So this will give us 2 multiplied by 3.142 multiplied by our F, 60 degree. Inductive reactance is 500 milli. That milli there is to multiply by 10 raised to the power minus 3. Take note of that. So when you press your calculator, all these will give you 188.5 ohms. Don't forget, inductive reactance, capacitive reactance, they are all measured in ohms because they are all resistance. So this is the first part. And the second part says, what is the current in the circuit? According to your Ohm's law, according to Ohm's law, voltage is equal to I multiplied by your resistance. Our resistance now is our inductive reactance, which is an SL. So that will give us our current from the question is what we are looking for. So we'll make it the subject of the formula. So let's make current the subject of the formula. So we have current here will be V over SL. That's what we are looking for. So our voltage is there is 120 divided by our inductive reactance 88.5. That will give us 0.6366 ampere. Take note of that.